So we have a site response analysis. We want to, in that we have 10 meters of clay underlined by 7 meters of dense sand. See table 1 for relevant properties. So I've purposely picked, just for some interesting results, some pretty soft clay underlined by dense sand with a friction angle of 38 degrees, and the clay has a cohesion of 20 kPa. A lot of the values have been quite simplified so that we're focusing on the kind of the process in FLAC and not on material interpretation. An earthquake ground motion velocity time history has been developed. In fact, I've given you acceleration, velocity, and displacement for the rock, so at depth. So that part has also been simplified. Using FLAC, determine the surface motion as well as the distribution of peak horizontal acceleration, velocity, and displacement. And the way that we're going to be modeling the clay and dense sand, and hopefully I hope that I hope that you all have the UBCHYST model, is with a, if not, we could use the more Coulomb model, but it would be nice to use the UBCHYST model. But we're going to use the UBCHYST model with a default N value of 2.5 and an RF value here of 0.98. So that's going to be our objective for this particular example, which will probably take us till around 6 p.m. So that's the goal. So let us switch. So this analysis, some of the simplifying aspects here is that we're again not going to have groundwater flow. We're not going to have total stresses. We are going to have dynamics, and we also are going to have the C++ UDM. So those are all going to be important items. What else? We're going to have 5 extra grid variables. And depending on what your last setting was, is that we want to use SI units. Now we can include advanced constitutive models. I think that's a good idea. So let's include that. So C++ UDM, dynamic, 5 SI, include advanced constitutive models, and OK. So I'm going to call this tutorial 6-1 and title tutorial 6-1 and OK. So the very first thing that we're going to do is develop our mesh. We don't need to use the virtual grid in this particular case. It's going to be rather simple for us to create it. But one thing that is going to be quite important is that we need to pick our element size appropriately. So one component would be we expect for there to be high shear strains in the clay relative to the dense sand because it is softer. But the other part that's going to be really important for us is that we are calculating a sufficient number of elements to be able to model the waves as they propagate upwards. So that particular calculation has been done in the tutorial statement. So if we go to the tutorial statement, let me get rid of the sidebar. So I have all this stuff, but the key thing here is that we want a few things. What we want to find out is, well, what size of our elements, what should be the size of our elements? And that's going to depend on a few things. So that's discussed briefly here. So it says, to determine the mesh density, the minimum number of zones need to be first determined. The maximum height of the elements required is typically assumed to be 1/10 of the shortest wavelength. For vertically propagating shear waves, we're going to use the shear wave velocity. What I've typically found is that I definitely would like my analysis, my elements to be such that I can pass frequencies up to at least 20 hertz. That's where a predominant amount of the energy from the earthquake is provided. So that frequency, that F max of 20 hertz, is then going to allow us to calculate everything we need. So what I've provided here, this is the shear modulus associated with the 3 zones, which was provided here. One important item in this is that this shear modulus is the maximum value that I'm currently using. I think an important consideration also could be, well, what would be a value, let's say, corresponding to E50, but at least in this particular case, I'm just using the elastic value. So we have shear modulus, we have density, so shear wave velocity is the square root of those two. Then we have F max. So then with F max and shear wave velocity, we can calculate the wavelength. So there is the wavelength associated with 20 hertz in those three materials. And so then what we want to ensure is that we have an element height that is less than a tenth of the wavelength. And so then what we're looking at the various materials is that, I believe that this is the clay, is that we want to ensure for accurate wave propagation that our elements are around 0.7 meters in height. Then for the sand, that they're 1.77 meter in height. And then for the rock, 5 meters in height. Given the thickness of each of those layers, a reasonable number of elements in each would be 14 elements in the clay, 40 elements in the dense sand, and really all we need is a single element, because we do need at least one element because it's going to be important for us to model the elastic half space of the rock. And that elastic half space, the only way we model that is by having at least a single element. So if you add up those values, we will get to 55 zones. One of the challenges in doing a one-dimensional site response with square elements is that some are going to be thicker, some are going to be wider, and so there's going to be a few little modifications there. So let's revisit this tutorial or this problem statement in a moment, but let's switch to FLAC and begin by developing our model. Okay. So what we're going to do, we could use the generate. That actually wouldn't be a bad idea, I suppose. But let's play around with a few different buttons. And so in this case, let us just use the grid. All right, so here's the grid. And so in that, we want a single element in the horizontal direction, and we would like 55 elements in the vertical direction. So 1 and 55. And then I'm going to click OK. So there's our mesh. One of the problems that we have, well, two problems that we have to first tackle this is first, it'll be important for us, especially for convenience of assigning material properties, to assign groups. And then also related to that, it's also going to be important for us to then resize this mesh, because currently the column is 55 meters high, and that's not what we want. We're going to have to resize some of these things. I'm also going to, before I lose some of these things, I'm going to save this particular state. And in this case, we'll just do one entire stage, this whole analysis in one. And so I'm going to call it seismic analysis as an example. Okay. So with that done, I have that. And now what I'm going to do is I'm going to click edit so that all of my button clicks are associated with this particular save file. So I want to assign the material groups. And so the simple command associated with that would be just group rock, j equals 1. So if I rebuild this, we will see that this bottom element is rock. The upper 14 elements is going to be clay. So that would be group clay. And so that would be J equals 42,55. Give us a top rebuild. And then everything between is going to be sand. So that's J equals 2,41. So there's our rock, our sand, and our clay. The next thing that we need to do is that we need to adjust the height of the elements. And so we will do that. We could have done it in the virtual grid if we'd wanted to, but I don't always use the virtual grid. In some cases, for meshes that are simple like this, I'll just use the, I go to build, I will then use the, not build, alter. I'll go to alter. So let's go to alter and then shape. So first key thing is that all of these 6 commands are in this particular file. We have clicked edit so that any click buttons get added to here, and then we're going to go to alter and then shape. So what I'm going to do is that I'm going to manually adjust the sizing of this. So we're going to kind of stretch things accordingly. Currently everything's 1 meter, and I'm just going to leave that. So the first element that we're going to adjust is the one at the bottom. So if we're going to zoom in on here, and this element, what we're going to say is that bedrock, we could make the decision on what elevation is 0, but I'm going to say the top of bedrock is at 0. So what I would like is the top of this particular element to be at 0. One thing that I find helpful as we're clicking on things is let's change the background color, and let's change the background color so that it is associated with the group. So I'm going to right click on the screen, I'm going to go down to zones, and then I'm going to go down to group. So we have cayenne and then blue. So what I'm going to do is I'm going to then click on this first element. So with this first element clicked, I can then move the nodes. I could do it manually by dragging this particular node around. But what I'm going to do is I'm going to right click on this node right here. And now what I'm going to do is I'm going to change the value of y. In particular, I'm just going to move this down to, say, -1. I'm going to move it down 1. In our particular example, I think I said that it had to be at least 5 meters in height. So I could make this a little bit larger, but I'm going to use -1 at least at this particular stage to make things kind of simple. So that moves that node down. Then I'm going to do that here. And this is going to be -1. I'm going to go above to this one. And this is going to be X and 0. And then we have right click here, and this is 0. So what we now have done is that we have the top of bedrock at elevation or at value of y equal to 0. One thing now is important before we move on to adjust the other materials is that we click generate. That is going to then assign a script or that's going to produce a set of code and also complete the conversion of this particular element. So I'm going to click generate. And the code associated with what we did is provided on the top left. So the next thing that we need to do is let's adjust the height of the, we're going to move the top. So if we look at the thickness of this deposit, the thickness of the deposit is 80 meters. This is currently at 55 meters. So what I'm going to do is I'm going to highlight all of the green elements here. So I'm going to highlight, and just as a reminder, the way I got that was I right clicked, I went to zones and then group. So I'm going to highlight all of these all the way down, and then I'm going to release. So now what I want to do is, with me zoomed in here, is now I want to adjust these nodes at the top first. So I'm going to right click on this one. I could do the other one, that would be fine too. And then this is going to be 80. You can see right now we've messed things up temporarily, and that is because, and it's telling us that we have currently bad geometry because of the element size. But we are going to fix that. And the way we'll fix that is we're going to right click on this node, corner 3. This is going to be 80 as well. And so now that part is going to be better. But what we do need to do though is that the base of the clay layer is at 70 meters. So I'm going to right click on this node. I'm going to make this 70. And then I'm going to right click on this node. I'm going to make that 70 as well. And then I'm going to zoom out. So reset view. And you can see it, at least we might have some issues here that we might need to sort out, but at least above here, this looks pretty good. So I'm going to click generate. Now, the problem that we have right now is that the dense sand, that element on the top of the dense sand has been stretched and a lot, and the one on the bottom has as well. One way for us to kind of refresh that is by simply highlighting all of the dense sand elements. And so what we're going to do is highlight all of those. What you can see is that it's tried to help us with deciding what the element size is going to be. So currently it's providing a mesh that is, the elements are smallest here and larger above. That's something maybe we want to do. But at the current time, what we want to do is just ensure that all the elements have the same height. The way that we adjust the relative changes in the element thicknesses, or in this case height, is with this center node, the center point. So I'm going to right click on the center point. And so currently what's happening is that all of those elements heights are getting multiplied by 1.04327 as we go above, which is why they're getting thicker. So instead of doing that, I'm just going to convert that to 1. And once I click OK, now you can see that now all of the elements are the same height as we go along. We do have a few little, issues that we could change. Is that we could make these finer so that there's less of a change between these two elements. But at least at the beginning, I think this is okay. So with that done, we're going to click generate. And so here is our numerical mesh. I'm going to include that code in the chat window in the event that you were having trouble with that. Then execute. So what we should have at the end of that is this code here. If you look at the code, you can see what's done is it's highlighted the values of j, and then it's gone along the 4 corners and it's adjusted the x and y value. So x and y, x and y, x and y, and lastly x and y as it goes along the 4 corners of these. Okay, so what we've done is we have assigned the material property, we have defined the mesh. The mesh is now conformed to our particular problem. What we want to do next is we want to assign properties. Well, let's first assign the properties to the bedrock. In doing that, I could go to materials and then elastic, but I think it's just as simple just to type them in. So what we're going to need to do is I'm going to say, okay, prop. And I'm going to specify the density. And this is going to be, all of this is going to be associated with the rock. So if I go back to the problem statement, the density of the rock is 2,200 kilograms per meter cubed. I also, on the same line, can also specify the shear modulus, and that's going to be the command shear. and the shear modulus is 2.2 e to the 9, which ends up with that shear modulus and that density. I believe the shear wave velocity is, in this particular example, is 1,000 meters per second. And then the bulk modulus that I've utilized in this case, which really is not going to have much effect on the material response, seeing as that the material response is primarily in the shear direction, is 6.6 e to the 9. And what we're going to do is associate this with the group rock. I believe that we could also add the not null as well. So the not null, the reason why we might want to use the not null, this actually came up when we were doing our stage analysis, is that we had temporarily removed certain groups and then added them. And so we might have a group, we might have rock in this analysis that we have nulled. And so we in that particular case, we may not want to specify the material properties to the rock, which is not currently in the analysis. So that's an additional option. All right, so that gives us that. Now what we want to do is that we would like to specify the properties associated with the UBCHYST model. Two ways of doing this. Option one is with button clicks. So let's go do that. So you go to Material and then Model. And so this is the place where we could have assigned the elastic, but we just typed it in. But in that, you can see that we have plastic. And because I have config C++ UDM, an additional option has been added. So that part's really important, that you have the C++ UDM. And that being is, if we go to Model, now we have this button here. So this was the one that we had looked at when we had explored North Sand, but now we're going to go to the user C++. And these are the three models that we probably have in our in that C drive. All right, so with that, we want DLL UBCHYST. So what we could do is that with this, we could specify it per layer, per region, per table, and per rectangle. I think the easiest thing for us to do here would be just per rectangle. And what we're going to do is just highlight those elements associated with the clay, and then also then those elements associated with the dense sand. Well, if you remember, the clay is right up here. If I want to right click on the screen and then go to zones and then go to group, so right click, zones, and then group, that will then provide you a reminder of the different groups. So to begin, I'll have that selected. I'm going to zoom in on here. I'm going to move that down a little bit. And then I'm going to drag from, I could go up or down either way, but I want to highlight all of those elements with the rectangular toggle clicked on the top right, and then I'm going to release. So here are the material properties for the UBCHYST model. The only two that really not much is going to be that different from what we did for the more Coulomb model. The variable names are slightly different, but really not much. I think most of them are fairly obvious what they are. So we're going to enter in these properties. The first thing that we're going to enter in is the bulk and shear modulus. Now, one important thing to note, pardon me, and this is an important distinction to what we did for the more Coulomb model, is that this bulk modulus and this shear modulus are not intended to be representative of, say, the E50 value, but instead they're intended to be representative of the value that you would say, for instance, determine from a geophysical investigation. the reason being is that the UBCHYST model then degrades that particular stiffness. And so we want to ensure that we are starting with the correct value. So if we toggle back and forth, although I'm not showing you the toggling, is that the clay layer has a bulk modulus of 1.2 e to the 8. So 1.2 e to the 8. A shear modulus of 4.7 e to the 7, 4.1 e to the 7, 4.1 e to the 7. Okay, 8 cohesion, which is the cohesion, that value is 20 kPa, so 20 e to the 3. All right, so friction angle is going to be 0, dilation is 0, we'll 0 the tension, strength here. All right, Hn, n is the factor which is going to affect kind of the curvature for which the stiffness changes. And so just to simplify things, I'm going to use 2.5. I do talk about how that value is selected and its impacts in the set of notes on constitutive modeling. And I'm also going to use, just to get us going, an RF value of 0.95. What else? These two values, this is the default value of this is 1, and this is atmospheric pressure, 101 e to the 3. I haven't noted any really impact on that particular, on terms of the numerics inside, but that should cover us in terms of everything that we need for the clay layer. So we have that. We then going to click OK. You can see then that code has been added here, and then we could click execute, but we might as well also do the sand layer while we're here too. So now what I'm going to do is I'm going to do the same thing, but then highlight those elements associated with the dense sand. Release. Interesting enough, it remembered what we did from the previous model, but for this, the dense sand has a bulk modulus of 7.4 e to the 8. 7.4 e to the 8. It has a shear modulus of 2.5 e to the 8. 2.5 e to the 8. 2.5 e to the 8. 2.5. Yep. And a cohesion of 0, but it does have a friction angle of 38 degrees. Because we're doing a fully drained analysis, any impacts of going from a drained to undrained situation, I think we don't need to deal with in this particular situation. All right, HN, RF, HPA, that looks pretty good. So the key changes here was 7.4 e to the 8, 2.5 e to the 8, and 38. Everything else is 0, 0, 2.5, 0.98, 101 e to the 3, and 1, and then OK. So those are taken care of, and then we can click execute. So I must say that this is a little bit silly the way that it outputted this. It's on one crazy long line, which is definitely very dissatisfying. I don't quite like that very much, but that's what it does. This is a classic case where once you look at these, you can see that, well, I could have typed in a lot of these things as well, but it's there. All right, so next up, what we need to do is that we need to specify our boundary conditions. What we'll do is that first we need to, with gravity, we need to calculate the stresses. And then after that stage, we're going to shake. So let's do that first. So in doing that, I want to model, I'm going to say, all right, I'm going to have K0 conditions. I'm going to have rollers on the vertical sides. I'm going to fix the base. I can click on the buttons, but I think in this case, it's going to be much quicker just to type, all right, I want to fix the velocity. Velocity is going to be initialized at 0, so it's not going to change. So I'm going to fix all of the elements. So that's just going to be fix X. I could say I could add additional, I could say I equals 1 to 2, but that is exactly the same as just doing that. And then I want to fix the y at the base. X is already going to be fixed based on the previous command. So let's rebuild that. And just to confirm that everything looks okay, there's all my x's, and then BB, meaning I've fixed both the x and y. We fixed it. And so then the next thing that we want to do is that we need to turn on and off a few toggles. One last thing we also need to do is specify gravity. So I could say set gravity 9.81, or if I want to click on the buttons, I believe it's utility. Nope, it's settings. So if you go to settings, then gravity 9.81. Interestingly enough, you can specify gravity at an angle. The only reason I've maybe thought that might be useful is if you want to, for instance, in the case of laterally, kind of like an infinite slope problem, where if you turn gravity at an angle, it's like modeling a slope. And that also should be 9.81, and then execute. Okay, so we have that. So all that looks pretty good. And so now we're going to solve. And I forgot something, didn't I? I forgot that one of the things that we didn't have a button click for is that we did not yet specify the density in the clay or the sand. So we need to do that. That actually wasn't included, because that material input is a material for all the elements. It's independent of the constitutive model. So we do need to say prop density, and the density of the sand, or let's do the, what did I do? The clay first is 1800 group clay, and then prop density 2000 group sand. And I spelled density wrong. There we go. And I forgot to do one other thing. So one of the problems that we have right now is that what this is highlighting is I'm doing a dynamic analysis. The reason why it's not reaching equilibrium is because I have no damping at this particular stage. So I need to click stop. And what I need to do here is that I need to set dynamic off. The reason being is that by setting dynamic off, I'm doing a, air quotes, static solve. The static solve uses local damping, which is applying a force in the opposite direction to the velocity of each of the associated nodes. So that's the last thing that I need to change. All right, rebuild. Okay, good. So the key things just to note as I've been changing is that I think we all probably, hopefully we're on the same page all the way up to right here where my cursor is that the density of the clay is 1800, the density of the sand is 2000. We need to fix the base. We need to fix all of the nodes from moving horizontally for like a level ground condition, fix the base, and then set gravity and set dynamic off. Okay, so at this particular stage, what could we do? Let's create a plot. I think maybe a first good one for us to plot would be, let's do to plot and then model. And I'm going to do state of stress. And in this, I'm going to, what am I going to have? I'm going to have the grid. And I'm also going to have, let's do displacement. So I'm going to click on vector and displacement. And I want to recolor this. So with displacement, which is going to be a vector, I'm going to click Edit. And maybe instead of black, make it blue. There's blue. And then OK. So at this current stage, if I was to click OK, I'd have my mesh and any displacement. But the other thing that might be nice in this is to go to principal stresses, tensors, and stress or e-stress. In this case, both will be the same. And then OK. What this is going to do is then add those crosses that are representative of the maximum and minimum principal stress. Oh, okay. Well, I guess blue was the same color. So maybe I'm going to change my displacement vectors to green because that is clearly hard to sort out what in the world that's doing. Okay, so I'm going to right click, click Edit, and then under displacement, click Edit again. Blue was a bad idea. Let's do green. Okay, this is a little bit better. So if we look through, zoom in, what we see here as this few key things to identify, which certainly seem to be the case, is that there is no lateral movement. This is kind of almost like this is in one big odometer test. The stresses are getting larger. There's no principal stress rotation, which also should be the case. And we're moving all the way down as we continue moving down here. The stresses keep getting larger. One of the plots that we could look at and calculate, well, maybe for instance, what is the K-naught condition? That's an extra grid variable that we could add if we so desired, but we can see the stress increase as we go down. I think what I'm actually going to do is break this up into 2 steps. I think that may be simpler and easier to follow. So let's right click on this and rename state. And I'm going to call this static analysis. And now what I'm going to do is that I'm going to add another save state, which will be the dynamic analysis. So I'm going to click follow. And this is where I'm going to do my dynamic analysis. Okay, a few things that we want to do. First up is that although I suspect that the velocities should be quite low, we might as well zero our velocities. So we can reinitialize our velocities as 0. We could go to the in situ, then initial, or alternatively, we could just say I would be initialize x velocity as 0.0, y velocity as 0.0, and then rebuild. So now another important question would be, well, do we want to zero the displacements? In many cases, what I've found for seismic analyses is that the pre-earthquake analysis, what we're primarily interested in is the stresses and not the displacements. Usually the models that we have are simpler, given the focus that we have on seismic analysis. And so in many cases, we also want to zero those displacements as well. So we're going to do that in this particular case. So we're going to be zeroing those displacements. And so with this, all these green vectors should disappear, and they do. So that part's important. So another thing that we're going to do is, and I think we did this for the simple shear loading condition, is that we need to make a few simplifications on some of the movement. And so one is that I'm going to say is I want this node and this node to move together, but move together. So if this moves to the right by 1 centimeter, I want this to move to the right centimeter and down as well. And so with that, the same case for these nodes. And the way that we impose that constraint is by going to alter. And then if you remember, it's the attach. It's kind of a funny application of attached. Usually we use the attach command to go from a coarse grid to a fine grid, but it also works well in doing what we want it to do here. So we're going to go to alter and then attach. And now what we're going to do is that I'm going to drag on the right-hand side, and then I'll do the left-hand side. So I'm going to click add a side. I'm going to go like this. Go to the very bottom all the way to the top and release. So I should have one big long red line, and then I'm going to do the same thing, but click B side. So I had A side clicked, and I'm going to click B side, and now I'm going to do the same thing, but now I'm going to start on the bottom right and drag all the way to the top and release. So if you can actually see what I have on my screen, I have a very, very thin red and green line that goes from the top all the way to the bottom. And then I'm going to click execute. No, I'm not. I'm going to click assign. There we go, assign. And so the key thing is with the command, you can see it says attach a side 1, 1, which is that node where I'm pointing right there, to 156, which is way up at the top here, from 2, 1, which is this node right here, all the way to 256, and then execute. So this is a constraint with the goal of trying to simulate a more or less simple shear type of condition. Okay, another very important aspect is that we need to allow our elements to move freely in the X and also Y direction, which are currently the case. So right now we have fixed the base and in both the X and Y direction, and we've fixed the nodes above that in the X direction. We need to free those nodes in the X direction, X and Y direction. But it's really important is that at least at this particular stage, we need to maintain the fixity at the base. And this will become apparent. I'll mention why, and this has to do with the quiet boundary condition in just a moment. So we need to free those nodes. So we could type, free X, that'd be fine. Or alternatively, we could also click the buttons. Let's do the buttons this time. So I'm going to go to in situ, fix, and then free. X and Y would work, or I'll just say free X. That should do. And what I'm going to do is I want to click all of these buttons. So if I drag from the bottom left, but being sure to exclude the very bottom set of nodes, and then drag all the way up to the top right, that should make all of those disappear. So I'm going to click there all the way up and then release. And what you should have is the command free X J256. So here we have that. That looks good. Okay, so we have that. We've done that. Okay, next thing that's important is that we're going to be doing a dynamic analysis, and we need to specify some type of damping. Thankfully, the clay and sand are modeled with the UBCHYST model, which does capture hysteretic damping at low shear strains. But nevertheless, it is important for us to have a little bit of damping. The damping frequency that I have found generally works, and I referenced a paper previously in the constitutive modeling notes, is around 2 Hertz. I feel like that does a pretty good job for the frequency range that we typically interested in seismic applications. And with that, what I typically target is on average about 0.5 hertz for models with a model like UBCHYST that does a pretty good job of capturing damping. And then I'll do on average 1% damping for the rock. So there's a few different ways of assigning that. The way that we are going to use that is with the, let's see, initial, I think, let's see here, dynamic damping. So the way that we're going to do this, I'm going to change it to code, but just to show you how to get this is if I go to in situ, initial, and then dynamic damping, is that this is the option. And again, what I went to was initial, in situ, initial, dynamic damping. Is that if I highlight a set of nodes, so for instance, I'm going to highlight the nodes associated with the core, which is from 80 to 70 meters, and then release, and then click assign. This is a place where I can assign damping. Now there's another place in the GUI where you can assign damping for the whole model. That's certainly one option, but what we want to do is we want to specify damping separately for the different materials. Here, I'm going to specify Rayleigh damping and the fraction of critical damping. This is the minimum value. I'm going to specify a value of 0.003. This will produce, on average, between about 0.5 and 20 hertz, a damping of around 0.5%. And the central frequency is going to be 2 hertz. In this particular case, we're going to use mass and stiffness proportional damping, which kind of creates that parabolic type of shape with damping ratio versus frequency. That particular variation I included in one of the presentation slides earlier this afternoon. So with that done, I'm going to do this, and then I'm going to click OK. So that's going to be that done right here. Now what we're going to do is that with the same in the sand and then also the rock. I actually find that this is fine with the J, but we can do the exact same thing with the group command. And so I'm just going to execute this and then utilize this command in a slightly different way. So with this being done, I'm going to click execute. Open this up, and instead of J, I'm just going to type group clay. The advantage of this now is that I'm going to copy this command and paste it below. And this is going to be sand. And lastly, this is going to be, I want to produce around 1%, and that ends up being, to produce on average 1% is about a minimum of 0.006. And this is for the rock. So let's rebuild this. So everything works fine here. And then I'm going to click save. I'm going to call this seismic analysis. Okay. So the next major thing that we need to do is we have changed our boundary conditions. Good. We've specified some damping. Good. Now the next and important thing for us to do is, well, we need to import our time histories. So let's go to here. All right, so I'm going to click edit so that all of my button clicks are associated with this file. And then what I want to do is that I want to open up this time history. The way that we do that is by opening this time history up as a history. So let's do that. So the place that we go to do that is go to Utility and then History. So this is the place where most of the time we're here, we're we're clicking on nodes or zones to tell FLAC, hey, I want to store information during an upcoming analysis. But this also happens to be the place where we can convert histories to table, and also we can read histories. And so that's what we're going to do here. So if you see that there's a read button on the bottom right, so click read. And this is where we want to then navigate to the particular. By default, it looks for a .his file. So let's click the down button and then all files. And so you'll see that these are showing up. What we're going to do is we'll at least open up the velocity. So let's do that. So click GMA velocity and then OK, open. And so it's done that. There it is right there. Hisread gm-a.vel.txt. And so we could do the same thing for the others as well. So I'm going to hit hisread, and I might as well, just for reference, because we might want to compare it to what we calculate, is the acceleration. So gm-a-acc.txt. So that's that one. And the last one that I'm going to read is going to be displacement. So we have hisread 1, his1, his2, his3, and we have all of those things right there. Execute. And so we'll click execute. So personally, I like to, when I am reading time histories into my analysis, I usually like using history 1, 2, and 3 for something that I actually want to calculate. And so what I like to do is, give this some number for which it's going to be fairly certain I'm never going to reach. I can't imagine myself having more than 100 time histories that I'm going to be storing. I could even do something more like 900. But anyways, I'm going to rename these history 100, 101, and 102. And then rebuild. So what I could do at this particular time is if I go to plot and then history, I could then put, say, input, so commonly input acceleration, time history, and time. And so in that was going to be 101. So I'm going to click 101 right here and then OK. And so this is the acceleration time history in meters per second squared. See that the time history is 90 seconds long. It has a peak ground acceleration of, let's see, what is that? It's 2.24. So 2.2. So 0.2, no, just a little bit up. So basically 0.25 G. But it has a fairly long duration. Okay, so we have that. So the next thing that we need to do is that this is the input acceleration. But what we need to do is we need to convert that velocity time history to a stress time history. The equation for that was discussed in the lecture notes or in the videos, and which I also have in the problem statement. So if we look at that, you can see that I talk about this here. So we're going to convert this into a stress history, and that's going to be that velocity times the density times the shear wave velocity, where that particular, the density times the shear wave velocity in this equation is for the bottom single zone, which is rock. So with that, the rock has a shear wave velocity of 1,000 meters per second. It has a density of 2,200 kilograms per meter cubed. If we multiply those two values, we get a value of 2.2 e to the 6. So what we want to do is that we are going to apply a shear stress that is going to be the velocity times 2.2 e to the 6. There's a few different ways of doing this. The approach that we're going to have is that we're going to apply a shear stress the magnitude of that, which is normally 1, is going to be not 1, but it's going to be 2.2 e to the 6. And we will be able to specify a history associated with that, which is going to govern how that shear stress is going to vary with respect to time. So let me show you how to do that in FLAC. Okay, so we are going to go to where we apply stuff, which is in situ, and then apply. So what we want to do in this case is that we want to apply a shear stress, and that's because we want to simulate vertically propagating horizontal shear waves. We're going to go to shear stress, and then shear, that one, stress, and then shear stress. Okay, that one. Now what we want to do is we're going to drag on the very bottom. So I'm going to go from the bottom left to the bottom right. Just going to look really little down there. Right there. And now I'm going to click assign. So in this particular case, what we're going to do is that first, and importantly, we are going to tell FLAC that I want the shear stress to vary with respect to time, and it's going to be varying related to the history associated with history 100. History 100 is the velocity. Now what I want is that I'm going to be using, so this is actually my multiplier. So there's a few different ways of thinking about this, is that I'm going to have a multiplier, and my multiplier is going to be varying according to the velocity time history. That velocity time history is going to be multiplied by a constant value, and that constant value here ends up being that rho times Vs term, which is 2.2 e to the 6. I'm going to click OK. And if we look at this, this HIST 100 part that's the multiplier, which is going to change with respect to time. The magnitude of that is equal to the velocity. And what we're going to do then is that value, which is going to change with time, is going to get multiplied by a constant, and that's the 2.2 e to the 6. So with that done, we're going to click execute. Okay. So what we have is this right here. Now, we have one last and very important thing to do, and that is to model the elastic half space below. One thing that we could play around with is that we could include the apply FF free field conditions, but we really are modeling free field conditions, so it's not going to have a huge impact. But what will have a huge impact is whether or not we are going to explicitly capture the elastic half space below this particular model, and that's going to affect how the waves are going to reflect and refract at that particular boundary. So the way that we're going to do that is with the apply X quiet and Y quiet. Now, one of the things that's really important is that it is essential that prior to imposing the Y quiet and X quiet is that we have this fixity here. What's going to happen is that once we apply the X quiet and Y quiet is that the forces that maintain equilibrium are going to be transferred to the calculations associated with X quiet and Y quiet. If we were to free these, we would erase that information, and in that, our model would actually be dropping through space. So it's really important that we include that at this particular juncture. So now what we're going to do is we're going to go to in situ, apply, and then I'm assuming it's under dynamic, and it is, and then X quiet. There it is right there. And we're going to just drag along the base and click assign. So that's the command here. And Y quiet, drag along the base and hit assign. And then execute. All right, so we have that. Well, at this particular stage, we're pretty much ready to go. A few last things that we want to do is that we want to set dynamic on and mechanical on, or set dynamic on, mechanical is always on. That would be a key item. And now at this particular time, we could solve for the 90 seconds. What I want to do is let's not solve for the whole time. It might take a little bit of while. Let's see what would be interesting is let's just solve for the first 30 seconds because what we're going to need to do and what we will do is that we are going to, while we're waiting for it to solve, we're going to add some additional bells and whistles to our code to be able to track various time histories. So I'm going to click solve, type solve, dy time. So that's going to solve to a particular time. And I said 30 seconds. And then rebuild. So a few things that you will see that will be a tad bit different from before. One of the key things that you see here now, which wasn't in the analyses that we've done previously, especially in tutorial 5, is that what we have now is a time step. That time step is 4.89 e to the minus 5. What I've found is that that time step is usually around, well, this is almost 1 e to the minus 4. I feel like that's a pretty typical value. If you have a full-blown analysis, a two-dimensional analysis, and you're getting, say, 1 times 10 to the minus 7 or 8, that is going to take a really long time, and it's something that you might want to rethink. Maybe there's a way that you can add some additional efficiency with your analysis. Okay, well, in my particular case, my analysis is complete, at least up to 30 seconds. So that is just at the very beginning of shaking. The one plot that we do have is the state of stress. And a few things for us to look at. First up is that you do see that there's a little bit of displacement. We have allowed our elements to move vertically, so there is that. We do see that there really isn't any kind of rigid body motion of our column, although it should be noted is that this entire model, it can move horizontally and vertically in space. That vertical motion we're allowing to occur so that we can allow the base to move up and down accordingly such that it is going to capture the elastic half space response below. So I'm going to save this. And now what I want to do is I'm going to add some additional features. The first feature that I want to be able to add is I would certainly like to be able to investigate the stress strain response at a few critical points, as well as the dynamics as well. For me to get to and calculate the stress strain response, I need to be able to calculate strain, and there is no strain variable. Instead, what we're going to need to do is create a little fish function that's going to compute the strain at a few particular locations. So let's do that. We've done something like this before. So the critical item would be for us to write this script before we solve. So I'm going to call this def_strain. One of the things that we want is for us to compute strain. We need to do that kind of funny thing where we create an array, 4 elements. Also is that we want strain to be computed every time step because we want to be able to plot these things with respect to time. So then in that we need the while stepping. And so then the common algorithm for us to do this, so the set of steps, is that we first use that function FSI. with FSI, then we will take the component of strain that we're interested in. The points that I'm going to identify is that I'm going to look for, I want to calculate the strain at kind of the center of the dense sand, at the top of the dense sand, and near the center of the clay. So just a few ways that we can remember ourselves what those are is I'm going to right click on this plot, click edit. One thing that might be nice is to add the group. That's going to add the coloring. If I run this as is, the group is going to be on the top. So I want to move that to the back of my plot. So I'm going to click up. And at this particular time, I want to have FLAC help me identifying what the I and J values are. I'll have those plotted for the grid numbers, so genome, and then OK. So this is a slightly busy plot, but what it will allow me to do is if I focus near the center, so this was 70. So if I look at around 35, I'm going to zoom in at 35. Here we go. So this element is element 22. I equals 1, j equals 22. So that'll be one place that I'll be interested in looking at. Another one will be up near the interface. So that would be, say, right here. Actually, you know what I think I'm going to do is I'm going to simplify this a tad bit, is that I'm going to just look at one more point, which is going to be right here at the very bottom of the clay. So that would be, that's zone 42. So the two, we have 22 and 42 are the two values of J that we're interested in. And in terms of acceleration, we're going to look at, I think the natural place would be this particular node, which would be 42. Another good one would be at the very top, would be 56. And then at the very bottom, which would be j equals 1. So we have a few time histories to add here. So we have a while stepping. We're going to use that kind of funny thing where we're going to execute FSI. And first up, it's going to be at 1 and 22. And we're going to pass into that AI. So that's going to calculate it in AI. And then I'm going to calculate the shear strain at 22, which is going to be 2 times the value of AI4. This is going to be executed at every single solution step because of the while stepping. And so this is going to be 42. And then that is going to be 42. So let's look at that. So we have that is that, and that, and that, and that looks pretty good. So we want to end that particular function. And because of the while stepping, we don't have to write underscore strain afterwards. This function is going to get continued to be executed over and over and over again. So now what we want to do is we're going to do some histories. First up is that as opposed to other cases, is that we definitely do not want to store the time history every single time step. Our files and this analysis is going to be quite small, especially with a time step of 1e to the minus 4. So let's see, what do we say? If we want a time step of say 0.02 divided by 0.02 divided by 1 e to the minus 5, putting this in my calculator. Oops. So let's do every, I think, what did I have? Every 1,000 time steps, I think, will be more than enough. Okay, so we got that. And now we want history. We want a few histories. In this case, we want dynamic time. So that's going to be time. That's going to be different than the time step. And then also hist. Let's do some of the ones above. So that would be underscore GX122. So that's my shear strain. And then might as well hist SXY I1J22. So that'll be nice. And then hist underscore GXY 142. That's the variable that was defined above. And then the shear stress. So that gets us that. Then we also might want to look at acceleration, hist x accel. And this is at the node location. So first up, and our expectation for the node is that the node 1,1 and the node 2,1 should be quite similar. So just by default, I'm picking those on the right, on the left. So that's that. And then, okay, the last thing that I have created, and we'll just open it, and this occurs, so call find ims.fis. And we're so close. So the last thing I want to do is I'm going to rerun this with the solve dynamic time off, just to be sure that everything's working okay. Doing that. All right, that looks okay. And then I'm going to click save. The one thing I do find at times is that sometimes I exceed the number of steps. I don't think this is going to be a problem here, but I think where that's set, let's see, where is that? This ends up being an issue when you have really, really long, as a really big number. And I think in my case, how many zeros? 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And then set the step as 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's specified in somewhere. I'm not sure where it is. It's somewhere in here. But that's also something I do too. I don't know if I can make that bigger. What happens if that happens? Oh, okay. So just basically a really big number. And last thing we're going to do now is we are going to solve this. Okay. So the earthquake record is 90 seconds. And this will be, we will be slowly encroaching on our 6 p.m. finish time, but we are almost there. As mentioned, I think the steps that we're utilizing here are going to be quite similar to the case of 2 dimensions. The differences that we would have is that, for instance, the attach, we wouldn't have that. That's just an artifact of trying to model one-dimensional site response. The free as well, that's something that we wouldn't want to do because we're going to be using the free field on the sides, which is something that we could test out here. So that's going to be a difference as well. Those are 2 differences. But we are going to have to initialize damping for the various models. That would be the same. We'd be specifying, we need to input in the key item here would be our velocity time history, which we're then going to multiply by the density times the shear wave velocity at the base of our model. We're going to have the quiet X and quiet Y. And what's important here is to note that we need to impose that with our fixities provided. We're then going to turn dynamic on So there's that. And then there's storing some stuff. I think another thing worth noting here is that, the selection of the constitutive model. In this particular case, I picked the UBCHYST model because it does a pretty decent job of capturing the G over G max with respect to shear strain. And you'll see that once we plot a few of these shear stress strain relationships. The UBCHYST model is not good at other things. For instance, it's still just the Moore Coulomb model. So in that, it's unable to accurately model the changes in excess pore pressure, the associated settlements and aspects like that, where a constitutive model such as NOR sand, PM4 sand would likely do a much more accurate job in doing that. So we're still waiting for that to complete. We're almost there, at least in my case. So what we'll do with the remaining time that we have, first thing I think would be worthwhile looking at some of the stress strain loops. That I think would be worthwhile. The other item would be comparing acceleration time histories as well. And then we also will plot the variation in the peak ground acceleration, peak ground velocity, and peak ground displacement. So mine's completed. Is anybody else's finished? Did it finish a while ago? So I'm going to save mine. So save my project. And now I want to add some additional, I want to plot the results. What I'm going to do first is let's plot stress versus strain. So I'm going to go to plot history. And I'm going to say something simpler like stress, strain. Sadly, this is something you can only do after the analysis is complete. Although you could clone something, but that seems like it doesn't work with the time history. So I'm going to do stress strain, round brackets, 1,22 to remind me where it's at. And then I want to plot average shear stress. So that would be for 22 versus shear strain, which is this one right here. No, there it is. It's right there. And okay. And so here is the shear strain, the stress strain relationship. And it actually doesn't look too bad. There is a little bit of bias as the shaking goes back and forth, I think also we probably would be worthwhile maybe decreasing the time step to show a little bit more curvature in terms of a few more points in terms of the stress strain loop. But what we do see is that there is that type of kind of hyperbolic type of relationship here. What I find also hard in terms of interpreting some of these results is recognizing where you start and where you end. I'm assuming, that we start at 0. And this is where adding, an additional, exporting this file and then importing and then running it in some software program where, for instance, you can have a color that's associated with the time, I find is often can be quite helpful. Okay, but that's in the dense sand. That's not bad. And then we go to history, and I'm going to add another one. And this one is going to be stress strain 142. And so that versus that, 5 versus 4, and then okay. All right, so we see a quite different response. A few things to note is that our engineering strain in this particular case is maximum value is just over 2%. And what we're going to find, and we will see this in just a moment, is that we have a layer where a lot of the high strains are being isolated between the softer clay and the stiffer dense sand below. So to explore that a little bit more, let's create a contour plot. I think that would be particularly helpful here. So I'm going to go to plot, model, and shear strain increment, I versus J. So I'm going to go down to contour zone, strains, and SSI. So there's the fill, and I'll add the grid so that I have that on top, and then OK. All right, so what we see is what we've, I hope, highlighted by looking at the stress strain is that we have very high shear strains isolated at the bottom of this clay layer, which is a typical type of dynamic response here, where we have these really soft materials. And that's being highlighted in terms of comparing the stress strain response at this particular point, which is shown right here, where we start here, it goes back and forth, but we get some really large loops. And then the point further down here in the more competent dense sand layer, and we're going to see a very different response. A few other things, maybe I'll just look at the displacements versus with respect to time at a few different locations at 1, 42, and 56. Let's go to plot, history, say X displacement versus T. And in that, I'm going to click Shift, or Control rather, and click these 3 time histories versus time, and then OK. So in terms of looking at displacement, a few things that we'll note. There's not a huge change versus the horizontal displacement between those 2 particular locations. This is in terms of meters. So we see that the black is the base. One thing that we do know is that there is a little bit of drift, is that the model starts at a 0 displacement, but the base of the model ends up having residual displacement at the end. And so one thing that's important to recognize is that when we look at the displacement at the horizontal displacement at the top, 56, that displacement is, I think it's not the absolute value of the displacement at the top is, if you look at the very bottom, is minus 0.02378. That's the absolute, the global value. But it's really important to, because of that shift, because of that kind of rigid body motion, is to subtract that particular value minus this value. So the displacement is that our model, the top, moved to the left at the end relative to the right. And that particular value is the difference between those two. So what I always like to do is that, especially in terms of displacements, is that I always will compute the displacements relative to the base of my analysis. This is also something, well, maybe the model, actually, the ground motion was baseline corrected, but there is just sometimes some natural shifts in that. We could also compare, so that's displacement. Let's also do acceleration. Versus time. It's a little bit hard to interpret with all the plots on top of one another, but what we do see is that there is certainly a difference between the black and the red. There's some amplification. We're also getting more higher accelerations longer in the record due to the response of that clay layer. All right, the last thing I want to show And then we will be the end is plotting some of these extra grid variables. In particular, let's look at the peak ground acceleration, which is represented by EX1. The way that we would do that is if we go to plot, model, and I'm going to call this peak horizontal acceleration with respect to IJ. That was calculated at the grid points. So grid points, extra, and then 1. That's fill and grid. And so what we're showing here is that this is the peak acceleration during shaking. So what we see is that there's a few locations where we have really high accelerations at the top of the dense sand layer, well, relative to the other locations. So this is in terms of meters per second, so just around 0.2 G. And then what we have is we have this soft layer, so the accelerations, deformations are larger above, but accelerations are lower because of the increased damping due to the yielding. So that's something worthwhile. Last thing I will show you, last thing for the course is this profile, which sometimes is helpful, albeit a little bit awkward, is if I click profile. What I can do is create a profile along a particular zone. The one thing that's a little bit awkward is that I want to plot things vertically, but it's going to plot things horizontally, but hopefully you could still sort it out. So I'm going to go to grid points, extra, 1. I want the orientation to be vertical, and I will show you what I mean. So what I did was I clicked here and dragged down. You can then move this around. I want it to go through here. What I'm going to do is I'm going to click create profile, and what that's going to do is that the horizontal axis is going to be the vertical distance. The vertical axis is going to be the peak horizontal acceleration. So the X and Y axis is a little bit weird. So you're going to have to rotate your head 90 degrees to the right to view this correctly. But if we say create profile, you can see that here is the variation. The one thing I think that's a little bit funny here, which I can change, is the number of sample points. I want more sample points. So 56 sample points, which is that button right here. Say create profile. That's better. So what we're doing is this is the very bottom of my model. This is the very top of my model. And so this is tracking. So I would need to rotate this 90 degrees counterclockwise. And so you can see the variation in acceleration versus elevation. And that's something you can do for all kinds of other profiles as well. So let's save the project. And so that completes kind of an introductory analysis of site response.